Hey guys, welcome to the Tutor Med channel. In this video, I aim to discuss how to interpret the iron studies the easy way. First, let's see the basic components of the iron studies panel. It is basically made of the serum iron, total iron binding capacity, abbreviated as TIBC, transferrin saturation, ferritin, transferrin receptors. Now, although the iron studies panel can be used to evaluate a number of conditions, our focus will be on how to differentiate iron deficiency anemia from anemia of chronic disease using the iron studies panel, because that is what is mostly tested in the exam. But we will briefly touch on how to use the iron studies panel to evaluate conditions like hemochromatosis, etc. And so if you are watching us for the first time and you love what you are seeing already, kindly support Tutor Med by liking and sharing this video and subscribe to our channel. And as always, my name is Dr. Obeng Frimpong, your Tutor Med. Good. And so like we usually do, before we go to any lab interpretation, we try to understand the basic sciences underlying the lab. Great. And so the food we eat has two forms of iron. We have heme iron and non-heme iron. Heme iron is usually found in animal products such as meat, while non-heme iron is usually found in plant products such as green leafy vegetables, tomatoes, etc. And it contains elemental iron, usually in the Fe3 plus form. And generally, heme iron is more readily absorbed than the elemental or non-heme iron. And so after ingestion, these forms of iron have to be absorbed. And I want to say that the site of iron absorption occurs chiefly in the duodenum. Although some can occur in the proximal jejunum, it occurs chiefly in the duodenum. And also, of the 10 to 20 milligrams taken a day, only 10% is absorbed by the body, although this amount absorbed depends largely on what the body needs. Now on this slide, let's have a brief look at how iron is absorbed in the duodenum. I should mention that although heme iron is readily absorbed, like I mentioned earlier, the mechanism of its absorption is not completely understood, although some authorities believe that it occurs through a receptor-mediated endocytosis. However, the absorption of non-heme iron is better understood, and so let's look at it. And so this is an enterocyte of the duodenum where iron absorption occurs. So I have just taken one cell in the duodenum, and that is it. Now, the non-heme iron, like I mentioned earlier, exists usually in the ferric form or Fe3 plus mainly. Now, Fe2 plus is better absorbed than Fe3 plus. And so on the luminal surface of the duodenal enterocyte, a protein called duodenal cytochrome B reductase converts Fe3 plus to Fe2 plus for better absorption. Now we have Fe2 plus, isn't it? Then another protein still on the luminal surface of the enterocyte called the divalent metal transporter 1, abbreviated as DMT1, now transports the Fe2 plus into the enterocyte. Now, in the enterocyte or in the duodenal cell, depending on the body's needs, the iron can be stored as ferritin or hemosiderin, or can be absorbed into the blood capillary. And so depending on what the body's need of iron is, the iron taken into the enterocyte can be stored in a storage form, or it can be transported into the blood. Now, the iron absorbed is in the ferric state, or in the Fe2+. There is a protein called hephaestin, which is able to convert the Fe2+ back to Fe3+, because we usually carry iron in the blood as Fe3+. And then after the iron has been converted into Fe3+, through an iron transporter called ferroportin, iron 3 is transported out of the enterocyte into the bloodstream. Now, though it seems like loads of information, I hope you can remember this, that the important players here are the duodenum and some parts of the jejunum, the proximal jejunum. These are the sites of iron absorption. Then the duodenal cytochrome B reductase converts ferric iron or iron 3+ to iron 2+. Then the divalent transporter 1 absorbs iron 2+. Then if the iron is supposed to be transported into the bloodstream, hephaestin converts iron 2+ to iron 3+. Then ferroportin transports the iron 3+ out of the duodenal cell into blood. Now, another thing we have to take note of is the fact that the liver is also involved in the regulation of iron entry into the body. It produces a protein called hepcidin or hepcidin during inflammatory states, usually chronic inflammatory states. Hepcidin regulates iron entry into the blood by blocking ferroportin. And so please take note of that the liver regulates the iron entry into the blood by producing hepcidin, which blocks the protein ferroportin. It is worth noting that although I have demonstrated that ferroportin is found on the enterocyte, it is also found in various cells, including macrophages and splenic cells as well. And so, whenever these cells contain iron and they want to release it back into circulation, depending on the liver's production of hepcidin, their ferroportins can be also inhibited as well to regulate the amount of iron in the blood. Please take note of this, because we will look at its importance when we are discussing anemia of chronic disease, which is basically a chronic inflammatory state. And so, like I hinted on earlier, ferritin is the physiological storage molecule for iron in cells, and it can be secreted into serum. Now, in healthy individuals, nearly all iron which is released into blood is bound to a protein produced by the liver called transferrin. And it is worth noting that one molecule of transferrin is able to bind to 2 ions of Fe3+. Iron barely exists freely in blood because it is toxic. It can cause iron-mediated injury to the body, and so almost every iron that is in blood is bound to transferrin. Kindly take note of that. Now I'm going to show transferrin using this hexagonal yellow figure. A transferrin transports iron after binding to iron, transports iron to tissues like the bone marrow, because we need iron in the bone marrow to form red blood cells, transports it to tissues like the liver, the spleen, macrophages. So based on this, we have parameters we want to discuss based on transferrin. And so the first parameter I want to discuss here is the total iron binding capacity, abbreviated as TIBC. The total iron binding capacity measures the iron carrying ability of transferrin, because we know transferrin's job is to bind to the iron which has been released into circulation. So we are measuring the ability of the transferrin to bind to iron. So it means that TIBC is low if transferrin is bound to iron. Because if transferrin is bound to iron, let's say we have a transferrin molecule which is bound to iron. If that transferrin molecule is circulating in the blood, its capacity is low because it is already bound to iron. Okay, so its iron binding capacity is low, principally because it is already bound to iron. Then you would agree with me that it is high if transferrin is not bound to iron. So let's say you have a molecule of transferrin which is circulating in blood like that. It is not bound to any iron. Then if you want to describe its iron binding capacity, you say its iron binding capacity is very high because it has spaces, it has portals for iron to bind to it. And so that transferrin will be described as having a high iron or total iron binding capacity. Now, before we move on, I want to make some statements about transferrin. Very important and then worth noting because we will need this in understanding the interpretation of the iron studies panel. I want to say that transferrin as a molecule is a negative acute phase reactant. What is an acute phase reactant in the first place? According to up-to-date, acute phase reactant by definition is any molecule whose concentration changes by at least 25% of its original value whenever there is an inflammatory process. And so if you're a molecule and your concentration increases more than 25% of your original value, let's say your baseline was 100 and during an inflammatory process you were raised by more than 25%, so you move to 130, then you are an acute phase reactant, but a positive acute phase reactant because your concentration changed by increasing. If your concentration decreases by at least 25% during an inflammatory state, then you are described as a negative acute phase reactant. And so because transferrin decreases in concentration during inflammatory states, it is described as a negative acute phase reactant. Now, although the term used is acute phase reactant, as in acute in the term, it does not only apply to acute inflammatory states, but also chronic inflammatory states. And so please keep this information, it will surely be needed. Very good. And so we have discussed the total iron binding capacity. And so now let's move to another concept associated with transferrin. It is transferrin saturation, and you know this is also part of the iron studies panel. And so what is transferrin saturation? Transferrin saturation measures how much of serum iron is transferrin bound to. Okay, and then transferrin saturation is highest when transferrin is bound to the maximum number of iron molecules it can bind to. And you'll see transferrin saturation is lowest when the transferrin is free. It means not bound to any iron molecules. So you know when we say a molecule is saturated with another molecule, we mean that the first molecule has been bound to the latter molecule. And so can you get the relationship between transferrin saturation and total iron binding capacity? You know, like I said, total iron binding capacity measures the capacity the transferrin has to bind to iron, whilst transferrin saturation tells us how much transferrin is bound to ferric iron. So it means that usually a high transferrin saturation, meaning transferrin bound to enough iron, translates to a low total iron binding capacity. And it makes sense, right? And then please get the choice of my words. I said usually a high transferrin saturation would mean a low total iron binding capacity, while a low transferrin saturation, meaning transferrin is not bound to iron, translates to a high TIBC, because if the transferrin has not been saturated, it means that transferrin molecule has a very high capacity to bind to iron. So usually they share an inverse relationship, although not all the time. It depends on the transferrin molecules available in circulation at that time. And so I want to share this formula with you. I got online that there is a formula for calculating transferrin saturation. Do not keep that in mind, but I just want you to know as an additional information that transferrin saturation is equal to the serum ion over the total ion binding capacity. That is the transferrin saturation, the formula. And so the last concept we need to understand before zooming into the interpretation of the ion studies panel is the transferrin receptor. Now, the transferrin receptor is expressed on cells and is used to import ion into those cells. Okay, and so when the bone marrow expresses the transferrin receptor, and so if the transferrin brings the ion from circulation, the bone marrow cells would use the transferrin receptor to bind to the ion and internalize it, and either store it as ferritin. If it will not be used, store it as ferritin, and this occurs principally in the macrophages, or it will be used to produce molecules like hemoglobin. So if you are producing red blood cells, we need a lot of hemoglobin, so the ion will be used, or it will be used to produce molecules like myoglobin, which is the pigment in muscle, cytochromes, etc. And so please take note of the transferrin receptor, as it is part of the ion studies. Now, so this is how I choose to understand the whole thing. I choose to understand this way that first of all, we eat iron. The iron is absorbed into the duodenum. It enters the bloodstream and it is bound to transferrin. And then the ion is picked up from the transferrin using the transferrin receptor, and then the ion picked up, depending on the cell which picked it up, is used to produce hemoglobin, myoglobin. It's stored as ferritin or hemosiderin, etc. And so this is how I choose to understand this when I am interpreting the ion studies panel. And so you may want to keep that also in mind. Good. And so let's see the various conditions that can be evaluated using the ion studies panel based on the understanding we have accrued over these past few minutes. Good. And so shall we? Now I am going to show you this table, and I'm going to put the parameter here, and the parameters of the ion studies panel. We have the serum ion, the total ion binding capacity or the TIBC, the transferrin saturation, the ferritin, and then the transferrin receptor. And the conditions I'm going to contrast here, okay, the ones commonly tested in the exam. So iron deficiency anemia, so I'm going to put that there, and then anemia of chronic disease. Now, in iron deficiency anemia, what happens to the serum ion? The iron is deficient in the body, right? And so we expect that serum ion would go low. Now, because in total or because entirely iron is deficient in the body, do you think that the total ion binding capacity should be high or low? Because iron is deficient in the body, the transferrin circulating in the circulation is free of what? Bound ion, because iron is deficient in the body. So you realize that those transferrin circulating, they are hungry for iron. So because of that, they have a high ion binding capacity. So since the ion binding capacity is low, what do you think the transferrin saturation will be? It will be, since the TIBC in ion deficiency anemia is high, then the transferrin saturation will be low because there is no ion for the transferrin to bind to in the first place. Let's come to ferritin. Ferritin is a storage form of iron. Entirely, there is no iron in the body. Do you think the body would like to store iron when the bone marrow needs iron? No. Okay, and so the ferritin stores will be depleted. Then let's come to the transferrin receptor. What do you think? Will the transferrin receptor be high or will be low? The cells which are expressing the transferrin receptors, like the bone marrow, they need iron. So they want to upregulate their receptors so that they can get the least iron they can get. And so they will show their transferrin receptor. So transferrin receptor will be high. And so it means that the picture you see in iron deficiency anemia is what? A low serum iron, a high TIBC, a low transferrin saturation, and then a low ferritin, a high transferrin receptor. Now, if you come to anemia of chronic disease, in anemia of chronic disease, remember that it is a chronic inflammatory state. And we said in chronic inflammatory states, the liver produces hepcidin, which binds to the ferroportin, inhibiting ion transfer into the circulation. So those cells which have stored iron as ferritin, they want to release iron into circulation, but their ferroportins are blocked. And even the iron we've eaten, the small intestines, their ferroportins are blocked. So you would expect that the serum iron here will be low. Now, if the serum iron is low, watch this. The TIBC, what do you think it should be? Should it be low or high? What do you think? The transferrin, should they have a capacity to bind to iron more? Remember that we said transferrin, this is where this information is important. Remember we said transferrin was a negative acute phase reactant. So in that phase, the liver will produce what? Little transferrin. So because the transferrin is even little in number, and then there is no iron to bind to, although there is no iron to bind to and the transferrin is little in number, you are still going to have a low total iron binding capacity because the molecules to bind to iron has been reduced because of the inflammatory process. And so what do you think the transferrin saturation should be? The transferrin saturation is also low due to the fact that there is no iron to bind to in serum, and then the amount of transferrin produced is also low. And so this is the unusual way time where we don't have the inverse relationship between the total iron binding capacity and then transferrin saturation. What do you think ferritin would be? The ferritin is expected to be normal because you see, it's not like we are deficient in iron, like iron deficiency anemia. What is happening is that because of hepcidin, those cells which have stored up iron as ferritin, they can't release the ferritin out as iron, and so the ferritin levels will be normal. And then the transferrin receptor is also expected to be normal because those cells have what? Iron in them. Okay, but the problem is that hepcidin is what? Preventing iron from being released from them, and so they don't feel like they are deficient in iron. They don't feel like that, and so they would not express more transferrin receptors. Very good. And so I hope the previous slide made sense. Now let's show another of this table. I'm going to put the parameters of the iron studies panel. So we have the serum iron, the TIBC, the transferrin saturation, the ferritin, and then the ferritin receptor. And then the conditions you are going to contrast here, actually iron overload and then acute phase reaction to any inflammatory process. What do you think would happen to serum iron in iron overload? Rationally, it's supposed to be high because there is what? Overload of iron. How about the total iron binding capacity? We expect it to be low because the transferrin has bound to a lot of iron, so it doesn't have the capacity even to bind. Then what do you expect of the transferrin saturation? Because there's overload of iron, then you have what? A high level of transferrin saturation. The transferrin has been saturated too much. Then what do you think of the ferritin? Because of a high iron in the body, the ferritin stores will also be high. Okay, so if you think along this line, you would understand iron overload, everything is high. The total iron in the body is very high. So how about the transferrin receptor? Do you think that they should express more transferrin receptors to pick up iron from the body? No, the entire iron stores or the entire iron level in the body is high. So those cells which need iron to produce molecules like hemoglobin or myoglobin, or to even store them as ferritin or hemosiderin, they have enough of the iron, so they don't see any reason why they should express more transferrin receptors as though they are hungry for iron when there is more than enough iron in the body. Now when it comes to acute phase reaction, You expect the serum iron to be low because, like we explained earlier, the ferroportin has been inhibited by hepcidin. Okay, so because of that, the liver produces hepcidin, which blocks all ferroportin channels, so iron can't come into circulation. And then we expect the TIBC to be low. Why? It is the same reason we gave for the anemia of chronic disease or chronic inflammatory state, because overall the transferrin levels produced by the liver is gone down, because transferrin is a negative acute phase reactant. Then you come to the transferrin saturation. I mean, think about it. The amount of transferrin even circulating is even low. So there is even low transferrin to even saturate. So it is naturally low. Then what do you think about the ferritin level? The ferritin level will be high because we have blocked all the ferroportin. Ferroportin is the channel through which iron in cells will come out. So if you blocked them because you are producing a lot of hepcidin, then you'll expect the ferritin levels to be high. Then we have the transferrin receptor. What do you think? Do you think it will be high? No, it's going to be normal. It's going to be normal because you see the hepcidin is blocking the ferroportin. These cells would have almost enough iron for their use, but they would not be hungry for iron like in iron deficiency anemia. Okay, so they would express their normal ferritin, their normal transferrin receptor. And so this is about it. Okay, you interpret the iron studies based on reasoning, rational thoughts, or rational assessment, analysis of the condition you are evaluating. And kindly pay attention to these three conditions: iron deficiency anemia, anemia of chronic disease, and then iron overload. These are the conditions usually tested in exams, so I've focused on these conditions. And so thank you for watching this episode of TutorMed. Please do not forget to like and share this video and subscribe to our channel if you love what we did. And then I will see you in the next video. Until then, bye.
Thanks for watching.